Part B of Module 2, Asymptotic Notations. Before we start this new topic, I want to complete the last part of the previous video when I talk about solving the element uniqueness problem. We use two different methods. Now we want to compare which one is better. So we will use this short video to compare two growth functions. Yeah. All right. First, let us look at where we are at this point. First, we just get the worst case counting functions from these two methods. Which one is better? Method 1, the worst case. So we get C1W of n, 1/2 times n minus 1. Method 2, CW2 of n log n. So remember the first part we use to sort the data to get the data organized. And we need to pay the cost. And we treat it as investment. Because after we pay this much cost, after that, we will enjoy the good result from this investment. So after that, we just only need to do n-1 comparisons to get the answer. All right. Now we need to do comparison. First, we get growth function of each one. For the growth function, first, we just keep the dominant term. First, let's take the dominant term. After we get the dominant term, then we drop the coefficients. We want to make it as simple as possible. So for that reason, we use n squared as its growth function for the first method. The second method, the dominant term, this is dominant term. Okay? Yeah. So the growth function is n log n. Now we just need to compare these two functions. Which one is increasing faster? Increasing faster means the algorithm is slower, right? Yeah. Algorithm is slower. Yeah. Yeah, because you need to do more comparisons. The more comparisons you do, you're slower. Yeah. All right. So now, to compare which one is faster here, we use the ratio to compare two growth functions. We use ratio to compare. Yeah. Limit and limit of the ratio. Yeah. The reason, so you may ask me why we use the limit here, right? Why we use the limit here? Because we want to look at the trend when n is large. Yeah. So look at the trend when n is large. That's the reason we take the limit. Why look at the trend when n is large? Remember the last time I explained when n is relatively small, the overhead takes too much portion of the total running time. So we don't like to, take in that way. So for that reason, we want to look at when n is very large. So we take the limit when n goes to infinity. Yeah. All right. Now, so let's do the calculation. Yeah. I hope you know how to do the calculation. How to calculate the limit. Yeah. First, let's do the simplification. Do cancellation. Cancel the common factors as much as we can So we simplify to n over log n. The limit of the ratio n over log n when n goes to infinity. How to calculate it? Do you know how to calculate it from your calculus class? No. All right. So here the log, although we do not have the base, because when you talk about log, you have to use certain base. Here we just use some general base a. This a, we want it only satisfy this condition, a greater than 1. The reason when a greater than 1, this log function is positive. So we want to look at a positive function. The growth function should be positive. So we don't want to look at the negative growth function, right? Negative growth function. So that does not make sense. So this is our reasonable assumption. Reasonable, all right. But in this class, most of the time, our A equals 2. Binary. So in computer science, we use the binary system a lot. So most of the time, we do the binary operation. So typically, we have the log base 2. All right, so here we just use the general a greater than 1 log base. Then we know this limit is infinity. Infinity. The answer is the limit is infinity. Some of you may ask, how to get it, right? How do you get it? From your calculus, if you can recall the details from your calculus, you can get it. But here, maybe I review a little bit because we need to do a lot of limit calculation. So using this chance, let me just try to help you review the limit knowledge. Method 1, we do variable substitution. Sometimes we can see the picture better with the variable substitution. Here, let us use a new variable u to represent that log function. U, because if we do this substitution, then we can get n equals a to the uth power. In this way, we change the form of the ratio. Okay, all right, so look at this. Now we can represent a new limit u goes to infinity, right? Because when n goes to infinity, u also goes to infinity. Okay? So we have this ratio. If you look at this ratio, can you get the answer? It is infinity immediately. Remember, a greater than 1. Can you get it quickly? Can you see that picture easier in this way? Here we can use the argument. An exponential function dominates any polynomial. So the numerator, this is an exponential function. Denominator, it is a polynomial, special polynomial. So we know exponential function with base greater than 1. So here we assume the base greater than 1. That kind of exponential function always dominate any polynomial function. If we can use that fact, we get the answer. But some of you, how do you show this is true, right? Some students may still ask me, how do you show this is true? We can show. If you want to see, I can show it, right? I can show it. So the next slide, let me show it quickly. In this slide, let me show you how to show it. All right. We need to use the Lobitas Rule. I don't know if any of you heard of it. because it is in Calc 2. Calculus 2, 1900. This topic is from Calc 2. Yeah. Some of you may not take it because it is not required. Yeah, it is not required for the new degree requirement. So many of you may not take it. So Lobitas Rule, but still, based on my experience, many students know Lobitas Rule. All right, so let us use it so we can prove it quickly. Yeah. All right, so our method 2 use Lobitas Rule to calculate the limits. All right, what's the Lobitas Rule? We can use, when we calculate limit of the ratio of two functions, then we can change to another form just to calculate the limit of the ratio of two derivatives of those two functions. That's the Lobitas Rule. Okay, yep, that's simple. But you need to know the condition. So there is a condition you need to check. Okay, the condition is the ratio must be one of the indeterminate form. Indeterminate form. So what's that? Infinity over infinity. So infinity, that means the numerator function goes to infinity. Okay. Oh, and denominator function goes to infinity. That kind of infinity over infinity. It's the form. Okay. Yeah. You know, simple representation, yeah, of the ratio format. Yeah. Another is 0 over 0. The numerator approaches to 0 and denominator also approaches to 0. This kind of forms we call indeterminate form. Okay, indeterminate forms. Yeah, S, right. Yeah. Many, we have many. Yeah. Even, and actually we have more, but these two are the two basic ones. So other forms for this class we do not use, so I do not mention other forms. Yeah. All right, now we are ready to do the calculation. The calculation is pretty simple. Yeah, just a few steps. Yeah. All right, first we check, yes, this ratio is the infinity over infinity indeterminate form. Based on that, we can apply the Lobitas Rule, take the derivative. The derivative of u, just the 1. Derivative of a to the uth, then you need to get the formula. Okay? Get the derivative formula. So that is natural log of a times a to the uth. Yeah. All right. So remember, a greater than 1, so natural log of a greater than 0. It's a constant. Okay? Yeah. Denominator 1, it's gone, right? Yeah, nothing. Divided by 1, nothing. Yeah. So you only look at the numerator. Yeah. A constant times a to the u goes to infinity, right? Yeah. A to the u goes to infinity. So the answer is infinity. Yeah. All right. So here, one thing I like to mention, I like to point out, when you apply the Lobitas Rule, you need to make sure you use the continuous variable. Why continuous variable? Then you can take, only when you use continuous variable, you can take derivatives. Otherwise, you cannot take derivatives. Okay, so you should be careful. Yeah. Here, let me use this example to explain this point here. Okay, important point. Mathematically, we want to do rigorous math here. All right, so look at this limit. This is an indeterminate form, right? Yeah. This is infinity over infinity indeterminate form. So we can apply the Lobitas rule. But before you apply the Lobitas rule, and this is not continuous variable, and can only take 1, 2, 3, 4, 5. Those are the discrete values, right? Discrete, not continuous. Yeah. So for the discrete variable, we cannot take derivative. If you take derivative, it's not a rigorous math. Yeah. So in our textbook, this part is not rigorous. Our textbook for this part, not quite rigorous. Yeah. So you should be careful. Yeah. All right. So, but how do you switch to the continuous variable expression? Do this way. We consider a new ratio similar to the old one, but a new ratio, we use x variable and we make x continuous variable. So not 1, 2, 3, so it can be any positive real number. This time it's a continuous variable, right? Yeah. Now we can take derivative. 1 over derivative of log base a, it is this one, reciprocal of natural log of a times x. After simplification, it is this expression. Okay? Yeah. Then when x goes to infinity, a constant, a positive constant times x goes to infinity, also infinity. All right. Now we show this ratio when x goes to infinity as a continuous variable, the ratio, the limit of the ratio is infinity, right? Yep. No problem. We prove it. Yeah. Finally, we get back to the discrete version. Because for the continuous version, it's true. Can we take x special values? 1, 2, 3, 4. Because for all x value, all real numbers, the ratio for x, the limit is true. Infinity is true. Then when we take special values, the limit also true, right? Special values goes to infinity, 1, 2, 3. It is also true. Infinity. So based on that, we can say it is true. This is the rigorous math way. Rigorous math way. We can take derivative here, but it is not good to do derivative directly on discrete variables. Not very good. So our textbook does that way. Yeah, so that's why you should be careful when you read the textbook, that part. Yeah. All right. Conclusion. Our final conclusion. Okay, yeah, final conclusion. Yeah. The algorithm with growth function n log n is faster than the one with growth function n squared. So method 2 is much faster than method 1. Because when n is large, the ratio goes to infinity. Method 1 much slower than method 2. So that tells us another conclusion. That tells us our investment to sort the data is worth the cost. Yeah. So it's a good investment. Good investment. All right, so let me finish this part.